Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on analytical dynamics or classical mechanics, chapter equations of Hamilton, lecture number 6, in which I will solve some problems by the method of ignorable coordinates. Now we solve a problem. Problem is by the method of ignoration of coordinates, solve the problem of a dynamical system with 2 degrees of freedom, for which T equal to T be the kinetic energy equal to half Q1 dot square by A plus B Q2 square plus half Q2 dot square. Potential energy V equal to C plus D Q2 square, where A, B, C, D are constants. Now we solve this. Since Q1 and Q2 are generalized coordinates, T be the kinetic energy of the system and T equal to half Q1 dot square by A plus B Q2 square plus half Q2 dot square. This is number 1. Potential energy V is given by V equal to C plus D Q2 square. This is number 2. Here A, B are constants, where C, D are constants. Therefore, Lagrangian function L is given by L equal to T minus V, implies that L equal to T is half Q1 dot square by A plus B Q2 square plus half Q2 dot square minus C minus D Q2 square. This is V. This is number 3. Since L does not contain the coordinates Q1 explicitly, but L contains Q1 dot. Therefore, Q1 is the ignorable coordinate. Lagrange's equation for coordinates Q1 is written as d by dt partial derivative of L with respect to Q1 dot minus partial derivative of L with respect to Q1 equal to 0 implies that d by dt partial derivative of L with respect to Q1 dot minus, since L does not contain the coordinates Q1 explicitly, therefore this derivative will be 0, implies that d by dt partial derivative of L with respect to Q1 dot equal to 0, integrating we get partial derivative of L with respect to Q1 dot equal to beta, a constant. This is number 4, implies that here if we differentiate L with respect to Q1 dot, here we will get half into 2Q1 dot by A plus B Q2 square. Here we do not get any Q1 dot, so this will be 0, implies that this equal to beta, implies that Q1 dot by A plus B Q2 square equal to beta. This is number 5. Now the new kinetic potential or Raoudhian function R is written as R equal to L minus Q1 dot partial derivative of L with respect to Q1 dot. This is number 6, implies that R equal to, here L is half Q1 dot square by A plus B Q2 square plus half Q2 dot square minus C minus D Q2 square. This is L minus Q1 dot, this partial derivative with respect to Q1 dot. Here we get Q1 dot by A plus B Q2 square. This equal to half Q2 dot square minus C minus D Q2 square. Here half plus half, and same thing here Q1 dot square by this. So here will be minus half Q1 dot square by A plus B Q2 square, and this will be equal to half Q1 dot square minus C minus D Q2 square minus half, we write A plus B Q2 square, multiplying this quantity with numerator and denominator. Multiply Q1 dot by a plus b q2 square whole square. This equal to half q2 dot square minus c minus d q2 square minus half. This is beta square. So we write here beta square a plus b q2 square. This is number 7. Now the problem is reduced to the solution of the single equation. That equation will be d by dt partial derivative of r with respect to q2 dot, because q1 be the ignorable coordinate. So here only remains one coordinate q2. Partial derivative of r with respect to q2 equal to 0 implies that d by dt partial derivative of r with respect to q2 dot is here half into 2q2 dot minus partial derivative of r with respect to q2. Here we get minus d into 2q2. Here minus half beta square multiply b multiply 2q2 and this will be equal to 0. Implies that d by dt 2 cancel, here q2 dot, here minus 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 plus 2d q2 plus 2 cancel, b beta square q2 equal to 0. Implies that this is q2 double dot, again derivative, plus 2d plus b beta square common q2 equal to 0. This is number equation 8. Since equation 8 is a linear differential equation, with constant coefficient, therefore we may get the solution as follow. q2 equal to a sine under bracket 2 dt plus b beta square to the power half plus epsilon bracket closed. This is equation 9, where a and epsilon are constants of integration to be determined by the initial condition of the motion. The equation 9 gives the required expression of the coordinate q2 in terms of the time t. Since q1 be the ignorable coordinates, therefore q1 dot equal to minus partial derivative of r with respect to constant beta. Implies that dq1 by dt equal to minus partial derivative of r with respect to beta. Implies that dq1 equal to minus partial derivative of r with respect to beta dt. Integrating, we get q1 equal to minus integration partial derivative of r with respect to beta dt. This equal to minus integration partial derivative of r with respect to beta is beta a plus b q2 square dt. Putting the value of q2 from here 9 and then integrating, we get q1 equal to beta a plus half beta b a square multiply t minus beta b a square by 4 2d plus b beta square to the power half multiply sine 2 bracket again bracket, this is curly bracket and bracket 2d plus b beta square to the power half t plus epsilon. This is equation number 10. In equation number 9, we find the value of q2 in terms of time t. Here also find the coordinate q1 in terms of time t. So equation 9 and 10 give the solution of the system. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.